In this video, we're going to look at some genuinely clever technologies and quite breakthroughs that are enabling small airships in ways that simply weren't possible before. From smart aerodynamics and new propulsion ideas to regulatory changes and energy systems that double as ballast, these innovations are turning what were once novelty aircraft into serious, practical machines. Airships make the most sense at large scale. That's why nearly all the airships currently under development that we hear about, the Airlander, the Pathfinder, Clipper, and Flying Whale LCAT, are massive vehicles with payload capacities measured in tens of tons. The reason is the square cube law. As the airship gets larger, its volume increases faster than its surface area. That means more lift for proportionally less drag and less exposure to wind. In simple terms, very large airships are far more stable than the small ones. This is why the giants, that is, the Airlander and Flying Whales, are the size of football stadiums. They're stable, efficient, and carry tons of tons. Small airships, by comparison, have historically been pushovers, too light to handle a breeze and too small to carry a meaningful payload. So that raises an obvious question. If larger ships are so inherently advantaged, why is there suddenly so much activity around smaller airships? And can we get smaller airships with payload not in tons but 10 to 100 kilograms? The answer is yes. Technology and regulation have finally caught up. Before we delve into exciting technologies, we should understand that one of the biggest enablers isn't even hardware, it's regulation. For years, flying a drone sized airship was a legal nightmare. You needed a specific waiver for every single flight. That changed with FAA Part 108 that was first announced in 2025 and updated in January 2026. Think of it as a license to roam. It's standardized beyond visual line of sight or BV operations for aircraft up to 1,320 pounds. Suddenly, the industry went from asking permission to move a mile to having a standardized framework for long distance autonomous missions. This single regulatory unlock has turned airships from science projects into commercial tools and have brought many small commercial airships into the mainstream. Instead of seeking waivers for every mission, operators can now fly routine long distance inspection, survey, and logistic missions under a standardized framework. The rule also introduces shielded operations, allowing aircraft to fly close to structures like pipelines and power lines, exactly the kind of slow, precise work airships excel at. With that regulatory foundation in place, small airships start to make a lot more sense. A great example is Kalu airship from Finland. Kalu is about 11 to 12 meters long and roughly 2 meters in diameter, around the size of a city bus. Despite its modest scale, it's been tested in Arctic conditions and designed to operate at temperatures down to minus 30 degrees Celsius. One key feature is its reflective upper coating. During the day, sunlight can cause internal pressure to rise. At night, rapid heat loss becomes a problem. The reflective surface acts as a thermal buffer, improving the energy efficiency that is critical for an airship designed to stay aloft for hours. Kalu is intended for border surveillance, wildfire detection, environmental monitoring, and mapping. It uses hydrogen as a lifting gas but incorporates patented safety systems to manage the risk. Kalu has a patent titled Variable Shape Design. This patent suggests actively changing aircraft geometry in flight. By adjusting internal stiffeners, the airship can become shorter and wider for more lift or longer and slimmer to reduce drag and fly faster. Instead of fighting the physics of small size, the aircraft can use the mechanism of adaptive design to its advantage. Another radical rethink comes from the Phoenix UAV. The Phoenix is a 15-meter long, ultra-long endurance aircraft designed to act as a pseudo-satellite. It doesn't rely on propellers for propulsion. Instead, it repeatedly transitions between lighter than air and heavier than air flight. The vehicle contains 120 cubic meters of helium, making it buoyant. Inside the fuselage is a separate air bladder. Pumps draw in and compress outside air, increasing the weight without changing displacement. This allows the aircraft to descend like a conventional plane. When the compressed air is released, the aircraft becomes buoyant again and climbs. The repeated cycle of ascent and descent, combined with careful vectoring of the lift and airflow, produces forward motion without traditional engines. It's a concept borrowed from underwater gliders and adapted for the sky. In simple words, the Phoenix breathes for propulsion. The energy for compressing air comes from the solar panels on its fins. Many of these new age airships are also converging on the same enabling technology, that is, fuel cells. In a conventional airship, weight is everything. Usually, as you burn fuel, the ship gets lighter and wants to float away, which is a problem. But a fuel cell kills two birds with one stone. Not only it provides power, but also provides weight for ballast. Using reversible fuel cells, stored water can be electrolyzed to produce hydrogen when additional buoyancy is needed, with oxygen vented overboard. When it's time to descend or land, the hydrogen is combined with the oxygen from the atmosphere to form water again. For every kilogram of hydrogen consumed, about 9 kilograms of water are produced, providing instant ballast while also generating electrical power. Combined with solar panels integrated into the skin, the fuel cells are the most perfect match for long endurance airships. Another compelling design comes from Cloudline, a South African startup developing autonomous solar power airships for last mile delivery in remote and infrastructure poor regions. The production version of the Cloudline airship is 18.2 meters long and 5.2 meters wide, large enough to be stable and efficient, yet small enough to operate autonomously under modern UAV regulations. Its mission set includes medical logistics, infrastructure inspection, wildlife conservation, disaster relief, and even temporary internet coverage where ground towers have been destroyed. Cloudline relies heavily on solar power, but one of its most interesting features is a yaw motor mounted on the tail. While the main hull mounted motors provide forward thrust and vertical lift, the tail rotor acts as a precision steering system. This gives the airship exceptional low speed maneuverability, allowing it to turn almost in place. Current models carry around 20 kilograms of payload, doing so with remarkable efficiency. As long as the sun is shining, the airship can remain in continuous operation. Battery power alone provides about 10 hours of endurance with range of 200 to 400 kilometers at a cruise speed of roughly 40 kilometers per hour. As of early 2026, Cloudline has moved from experimental prototypes into production ready designs. At the upper end of the small airship spectrum are high altitude platform systems or HAPS. These aircraft operate in the stratosphere, carrying payloads of around 250 kilograms and generating roughly 10 kilowatts of solar power. Unlike balloons, they can station keep, and unlike fixed wing UAVs, they can carry large payloads for months at a time. A typical example is a 65-meter long aircraft capable of covering regions roughly 100 miles across for extended periods. Its advanced laminated hull is several times stronger by weight than traditional materials and dramatically more gas tight, allowing helium to be retained over months-long mission while surviving intense UV radiation and ozone exposure. Beyond these, companies like 82 Aerospace are developing hydrogen-powered cargo airships designed to land on unprepared surfaces, while projects such as Solar Airship 1 aim to fly around the world without fossil fuels, using solar power by the day and hydrogen fuel cells by the night. Those larger airships deserve a video of their own. But the takeaway is clear. Small airships are no longer novelties. Thanks to smarter aerodynamics, novel propulsion concepts, solar power, fuel cells, and finally, sensible regulation, they're becoming practical tools filling roles that no other aircraft can do as efficiently or as persistently. And with this, the video is concluded. If you learned something from it, then please do give it a thumbs up. Thank you for your attention.